started. I'll keep this discussion relatively brief, but I'll be talking about Electrovaya and our experience with cycle life, and specifically because this is more of a research conference, talking about next gen batteries and the challenges there are with increasing with cycle life specifically. So just as a safe harbor statement, Electrovaya is a public company listed on NASDAQ, so we generally always put this out. But just for those who don't know what we do, Electrovaya is a battery cell manufacturer and battery systems manufacturer. And we also call ourselves a technology developer there. We have been in the lithium-ion battery space for over 2 decades and have a significant IP portfolio that's built up over time. But today, the company is really built around a key technology, which we now call the Infinity battery technology. This was developed around 2017, and it is a technology which significantly enhances the safety and longevity of lithium-ion batteries. I would say it's a platform technology, somewhat agnostic to the chemistry used in the cell. And we've applied this technology mostly to heavy-duty applications, things like robotics, warehouse automation, even forklifts, and certain sort of niche defense type applications as well. So why are these applications interested in this technology? Well, these are applications which typically are very sensitive to cycle life. If you look at warehouses, they'll operate 24/7. They may do multiple cycles on a battery per day. These are often automated devices which cannot easily be maintained. So having that increased cycle life really provides a benefit. The other is, of course, they're operating indoors. And when you operate indoors, doing multiple charges a day, cycle life, safety is paramount. And so one of the key technologies that enables the improved safety of our batteries is our separator technology. This is I would say we call it a ceramic separator, and in fact, it's over 90% ceramic. And so it's stable at high temperatures. This greatly enhances the thermal stability of our cells, and we believe that this is the key component which is enhancing our safety side of things. So if you took a look at typical lithium-ion battery separators, they will shrink at higher temperatures, just like most plastics will. And when that happens, of course, you get a short circuit in your cell. In our case, the ceramic is stable at much higher temperatures and really enhances that safety element. We've made over, a couple million cells using this technology and have had zero failures, over 35,000 battery systems with this technology as well. So safety is key there. And then obviously that has great importance for anything, again, operating indoors, data centers, uh, anything that's near a building. We believe that the desire for this type of technology for automotive is less strong. I mean, of course, you want your batteries to be very safe, and most batteries, of course, are very safe. But the zero tolerance type situations are those that are operating indoors. The technology also has led to enhancement in cycle life, and we've done this through a variety of ways, essentially reducing the parasitic reactions that take place in the cell. So why do typical lithium-ion batteries degrade? Well, there's a lot of side reactions which occur with the anode, with the electrolyte, with residual moisture, all sorts of, it's a very complicated system, as you well know. And for these graphite-based systems, we've managed to really reduce that parasitic reaction substantially, and that's what leads to this improved cycle life. So as a company, this is new technology. If you look at the overall battery space, there are, I'd say, simplifying it to a high degree here. There are the traditional battery manufacturers who are very focused on automotive, and secondary would be grid scale energy storage. And these companies are very good at developing technology, no question. But most of that technology is focused on cost reduction. And dollars per kilowatt hour is the most important metric for uh, these types of batteries. And they've been successful at driving down the price substantially just over the last 10 years. And that's enabling electric cars, great things. Electrovaya is not trying to compete in that. And this technology is not competing with that sort of traditional lithium-ion battery chemistries. There are, of course, many new companies in with silicon anodes, solid state batteries. These companies are very focused on very high energy density. And it's a very exciting space, no question. However, there are challenges for this type of technology. I'd say these challenges have not been proven at a commercial. The solutions have not been proven at a commercial scale. I don't know of any, full silicon anode cells being used in high volumes yet. Same thing with lithium anode cells with aiming for this 1,000 cycle number, right? So if you want to have a cell used in a defense application, yes, you can have a 200 cycle cell and it would be fine because they're generally looking just for uh, very high performance, and life cycle is not important. But if you want this next gen technology to be used in cars, if you want it to be used in um, your phones, your laptops, etc. Reaching that 1,000 cycle mark is absolutely critical, and it's challenging, no question. So we ourselves have developed are working on a solid state battery. Well, if you our current commercial cells are use a ceramic separator, as I mentioned, and for our I wouldn't necessarily call it a solid state cell. I would say it's a lithium metal based anode. But will utilize a ceramic separator. The main difference here is that ceramic separator is ionically conductive. We're getting decent conductivity there and making cells. But the cells, no question, still have a challenge with regards to cycle life. I'm sure we'll find more challenges as time goes on, but that's number one in terms of, I would say, a commercial barrier. And so I just put down some thoughts here, and yourselves would love to hear your thoughts as well here. But with regards to solid state batteries, this also applies to silicon anode batteries, lithium metal anode batteries, any of these next gen cells where you're trying to push the envelope to 350 to 500 watt hours per kilogram, and that 900 watt hours per liter number, which is what many companies are looking to get to. What we see and what I see the challenge is around cycle life, and that stems from lithium metal being very reactive, dendrites, side reactions, all sorts of challenges. And so again, simplifying it to like four mitigations, which I think are probably the best ways to solve this would be number one, you have physical barriers, right? A physical barrier to stop the dendrites. So that's a ceramic material, that's a sulfide material, something like that. Uh, to work with the lithium to 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 mitigate the dendrites. Number two there, solid state ion transfer. That's just instead of having liquids transferring your lithium ions, you have a solid there. That sort of goes in tandem with the physical barrier, and that's why. these ionically conductive separator materials are so interesting. Number three, chemical mitigations, right? So personally, I don't view a full pure solid state cell as being practical. You have challenges with regards to the cathode, especially in terms of reaching further into the structure. And so you can utilize empty space with some potentially chemical mitigation methods. And then finally, these cells, whether you're using silicon, lithium metal, or even tin, you will have significant changes in dimensions of the electrodes as it cycles. And so physical pressure is often used to mitigate, improve the cycling amongst other methods there. So this is simplifying it. However, it's definitely challenging. I'd say you may solve this on single layer cells, single layer, coin cells is one thing, multi-layer cells is another. And the larger the surface area, of course, the more difficult it gets. I've seen large companies, even multi-billion dollar companies talk about their technology and think it's ready for prime time, and then it turns out it's not. So the the validation of this is lengthy, difficult, and so a lot of smart people are obviously working on this, and I'm sure solutions will be made. But today, my opinion is nothing quite meets the numbers. Otherwise, you would see it. But with that, I'd love to, have other people input here and have a brief discussion.